So as Avi said, I am Shawn Domagal-Goldman. I'm at NASA Goddard Space Flight Center down the hall from Vincent, who you just heard from. And I'll be talking about Atmos, which is a 1D for altitude, that's the dimension we cover, model for the chemistry and climate of exoplanets or solar system worlds or Earth through time. Historically, it's had its roots in studying problems of Earth history and Mars history, and then adapted to do exoplanet relevant stuff. I'm probably missing some names on this list of names below. I try to catch all the people that have worked with us at Goddard over the years on this code um, for short stints or longer stints. There's a longer list of people that have helped contribute to this code that are collaborators elsewhere, namely at UC Riverside, where Eddie Schreederman's team is, and they've been using the model quite a bit and also helping improve it. Let me just start with kind of what Atmos is used for, at least now, most commonly, which is it really generates self-consistent atmospheres. So it studies the chemistry and climate of these exoplanets, but it generates atmospheres where the chemistry and climate are consistent with one another and consistent with the boundary conditions you give the model, which I'll get to later. And we can then send that over to a tool like PSG, which you just heard about, to create spectra of what those exoplanets might be like. But when we generate the spectra, if they come out of an Atmos model, there's that self-consistency to the atmosphere when the spectrum is generated. And so this is like figure 1-1 in the Astrophysics Decadal Survey. It was in the LUVOIR and HABEX reports. And as you'll see in a couple slides, the spectra that were in here, they were generated based on atmospheric models we built inside Atmos. Oh, this is some animations for the LUVOIR talk that I didn't need. The two things that it's probably most well known for are the thing I just talked about, generating spectra of these model atmospheres that we can then, I'm sorry, generating atmospheres that we can generate model spectra for. We don't do the spectral modeling ourselves in Atmos. We hand it off to partners elsewhere to do that. But we generate those atmospheres. So we're well known for like the pale orange dot series of papers that Jada Arney wrote when she was first a grad student and then a postdoc and early career civil servant at Goddard. And also the climate side of it has been used to define the habitable zone, at least the 1D models that went into defining the habitable zone. And I think those are the best known pieces of work. So this is the climate model that we have, and I should be explicit here. There's a climate model, which does the 1D temperature profile, and a photochemistry model that gives us the atmospheric chemistry. And what we can now do for the last 10 years or so is we couple those together loosely. We have an algorithm that runs that one and then runs the other, and it keeps doing that until neither of those model outputs change significantly between one run and the next. But the climate model is the same one in its roots that Ravi and teammates used for the habitable zone calculations. We're still doing research with it. I'm not going to go into detail on this here, but just so people know, we're still thinking about mission implication work with this tool, and we're not the only ones using it. I'm just highlighting the early career people from our group that have left recently. Ryan Felton has done some nice work changing the upper boundary fluxes. You can change the fluxes into the model, which I'll get to the inputs and outputs in a bit. He's showing how if you put some atomic oxygen flux into the top of the atmosphere, that could have an impact on the bulk chemistry of that atmosphere. This is thinking about a Titan-like world that's getting oxygen atoms from above, similar to how Titan gets oxygen atoms that originate out of Enceladus in our solar system. And then on the right here, we have Monica Vidari's recent work defining a Venus zone and showing that it could overlap substantially with a habitable zone. So this work is still occurring. This is with the photochemistry model primarily on the left and the climate model here on the right. And there's lots of other people in the community that use these things. So how does it get us those results? I'm going to give a simple toy version of what Atmos does first for photochemistry and then climate. Let's say you want to know how much ozone is in a given layer of a planetary atmosphere. Well, to know that, you would need to know if there's nothing in that atmosphere other than ozone O2, molecular oxygen, and atomic oxygen O, you would need to know how much O and O2 are in that layer of the atmosphere because O and O2 can participate in reactions that generate O3. Conversely, how much O3 is in the atmosphere is going to determine how much O and O2 is in the atmosphere because reactions of O3 can drive the O and O2. These things are kind of in a cycle of reactions that form each other from each other. Additionally, you'd want to know how much ozone was in the layer above and below the layer you're interested in. And for oxygen, both molecular oxygen and atomic oxygen, you want to know how much of those gases were in their neighbor layers. And so if you just had a version of the model that had, say, 3 species and the small number of reactions that connected them and 3 layers, this is what the Atmos model would contain, those 3 species and 3 layers. In reality, we generally have around 100 species in a given run, and we generally have about 400 reactions connecting them, and that happens over about 100 to 200 grid layers in the model. And then on the top and the bottom of the model, we add our boundary conditions. At the top of the model, that's primarily energy coming in from the star. We can give a spectral energy distribution. We've got model stars in our database that you can just call up, including M, F, G, K stars, and a variety of M stars, because they're like toddlers. They're hyperactive and each one's unique. And we also can introduce boundary conditions, usually for molecules at the lower bound of the model. We can flow stuff out through the top and in through the top, but most of the action there happens at the bottom of the atmosphere. We can simulate biology through a flux of gases or volcanoes through a flux of gases, and we can also simulate non-biological processes such as dissolution in ocean water or reactions with rocks. None of that's done explicitly with like a geochemical or ocean model at the bottom. It's all done implicitly through the boundary condition choices that we make. So that was for the photochemistry model. I said this is really 2 separate models. The climate model, I'm going to try to give a simple toy version for that as well. Imagine you want to know the temperature in a given layer of the atmosphere. Well, to know that, you would need to know how much oxygen and ozone is in that layer of the atmosphere, because oxygen and ozone can absorb incoming solar radiation as well as outgoing IR radiation emitted from the planet. And if that is absorbed in a layer, that layer is going to heat up. And of course, you'd also want to know the temperature and the pressure of the neighbor layers, because that can control advection and convection, and as well as diffusion. So you want to know the temperature and pressure in each neighbor layer, and then you want to stack that together, and you get this sort of set of couple differential equations that gives you the full solution. And again, we have boundary conditions here. The biology one is not explicit in CLIMA. The main boundary condition here is the solar flux at the top. There's really nothing coming into the climate model at the bottom. What the climate model receives in terms of the molecules is it gets the molecules from photochemistry, including aerosols. We can do aerosols in this model. It gets aerosols from the photochemistry model and a molecular species profile from the photochemistry model. It calculates a temperature pressure profile based on those things and a water vapor profile, and it passes those things, the temperature, pressure, water vapor profile, back over to photochemistry, because many of the chemical reactions are temperature, pressure dependent. And water is also a major player in our photochemical network. So those things get bounced back and forth iteratively between the 2 models until we have a self-consistent solution. In terms of inputs and outputs, these are the main ones. There's quite a bit you can tweak inside the code, but usually we guide people to start with thinking about the molecules you want to study in your atmosphere. You have to think about your boundary conditions, both for the molecule itself, and really what I tell my students is you have to be empathetic for the planet here. You have to imagine you're the world you're going to simulate, and your boundary conditions have to be set up understanding what that world is experiencing. You need the chemistry network that connects those molecules. If you are using molecules we already have in the model, you can just use our pre-existing chemistry networks. You need to explicitly define the chemistry network when you're adding to the model, and that's really for, I would say, expert users. You're going to need some time to do that. We don't have the model set up in a way that makes that easy, unfortunately. You also can specify planet properties, radius, gravity, the net total stellar flux, etc. And separately from that, you can define the stellar spectrum, and the stellar flux can be sort of modulated according to the stellar spectrum you provide. In terms of outputs, you get the 1D temperature and chemistry profiles. You also get the fluxes across the surface, as well as some detailed things like how fast things are raining out and stuff. Most importantly, to me at least, is that this stuff is self-consistent. We really focus on making our models a self-consistent solution. not necessarily like the answer. It's not, we don't think of this as like, we've got the model for TRAPPIST-1 or whatever. It's like we've got a model of it that numerically works and where the physics and the chemistry are self-consistent for the processes we include. If you want to get started, we do have a public version of this on GitHub. It's on the VPL repository under Atmos. What we usually do is we test out new model features in our and get them published in our papers. I'll be honest, the code's a bit of a mess. It's not great to go and do deep dives in and modify. We've been doing a lot of work over the last decade or two and making that easier, but it's been really hard because this is one of those codes that goes back to like Hollerith labels and all this like nasty Fortran 60 in its original version that I inherited. We have modernized the Fortran as much as we can, but my advice is if you want to run the model and edit the guts of it, I suggest getting in touch with, if not our team, someone else like Eddie Schwederman that's run the model quite a bit before. If you do want to get started with little help from us, we have some YouTube tutorials. They're the only videos that exist on my YouTube channel. So if you go to my, just find me. I'm not doing this for like the likes or the subscribes or anything like that. These might be the only 3 videos I ever put up on my YouTube channel. But you can get some tutorials there that teach you all about the inputs and outputs. I might do a part 0 at some point that give you the starter tools like Git that you need to get started. That said, and I don't want to like negate everything I just said, but like there is a way better version of both of these models that have been created by Nick Wogan. He's Pythonized a lot of our Fortran code, keeping a call to a better, faster numerical core. I think is C, or it might have been Python, I can't remember. Nick is a grad student, so like I want to be cautious and not sending like the whole world that wants to do photochemistry climate stuff his way. But like he really did an amazing job taking our code, making it more modern, making it more editable, and also he changed out the numerical core for photochem in a way that dramatically improves its capability to do things like time-dependent simulations, which we couldn't do before. So if my advice is if you're getting started and you want to do something we've done before, like we've done in the literature, and you want to take a different spin on it, you can do that with our code. If you want to do something that we haven't done with our model before, I think that's going to be more easily done with Nick's version. And we're starting to direct our own students to start to use Nick's version as well going forward. I mean, we're using our version, frankly, out of habit and out of our lack of time to learn new stuff. So I'll stop there. Check out our code on GitHub or Nick's versions of the codes on GitHub. And if you have questions, hit up our YouTube channel or email us. Thanks.
Thanks, Shawn. Let's give Shawn a great hand for a great presentation. Exciting code. So questions, of course, if you please raise your hand, your virtual hand, if you have a question, or put one into the Discuss Talks chat. Nestor Espinoza has a couple different questions. Nestor, I don't know if you want to jump on and ask.
Sure, I can, yes. Thanks, Shawn, for this amazing talk. We're super excited to start using Atmos with some students. And I have 2 questions. The first one is, how much does a model take to cook, quote unquote?
Yeah.
Both in the case in which you reach convergence right out of the box, but also in your experience in which you're trying to reach convergence and you try, handful different models or tens or hundreds, I don't know how much it takes. So can you maybe, some words on that end?
Yeah, generally, if the way the model works is you give it a guess for the atmosphere, and then it finds a self-consistent atmosphere that's stable on the time scale of the universe. If your guess is close to the answer, it takes seconds to tens of seconds. If your guess is far from the answer, it takes minutes to maybe an hour. And sometimes it just never converges. So it depends how good your guess is. To the second question, we have Jamie Krause, who's been doing that for Exoplanet grids. Eddie Schwederman has a student that's been doing it for some Earth-related grids, and then Sandra Bastelberger, one of our just amazing postdocs, has been also working on our key into modern Earth grids. So maybe we can get in touch offline or online about that.
Awesome, thank you.
Yeah.
Okay, thanks. So Sean, one more, I think Sucrit has one more question that was somewhat technical here, but the validated Venus photochemical template. I put it into the chat. Maybe
I don't think we do, Sucrit. That's something I've wanted to do for a while. Oh, Nick does. Of course Nick does. Nick is amazing. Like if you want something, like you ask the question, either Nick has done it or he'll get it done in like the next like 3 months. So we don't in our version, but Nick does in his.
Great. Thanks, Sean, and thanks, Nick, of course. And of course, all the Atmos users and contributors. Great resource.